Adversarial from LMU.
Hey, I'm Benno Kroyer from LMU.
And I'm Dennis Pescott from the University of Vermont. We'll be presenting our paper which introduces ContraCAT.
ContraCAT, we looked at coreference resolution in machine translation, where the reference crosses the border between one sentence and the other. Let's look at an example. The cat ate the cookie. It was hungry.
But why should you care about this? Because coreference is an important part of machine translation and often has a clear right and wrong answer. To stick with our cat theme, imagine this sentence. It ate the cookie quickly. In German, it can be translated into es, or sie, depending on context. It's impossible to know which one this refers to without context. If you saw the earlier sentence, the cat ate the cookie, you would know that it refers to cat. We study coreference translation in two ways. First, adversarially attacking ContraPro, a German-English pronoun translation dataset, and second, creating a series of templates that we call ContraCAT, that are meant to test the steps of a hypothetical coreference pipeline.
In order to thoroughly test pronoun translation, we propose the following hypothetical coreference resolution pipeline for machine translation, which consists of three general steps. First, let's take a look at the example on the slide. The cat and the actor were hungry, it was hungrier. The first step of our pipeline is markable detection with humanist filtering. In this step of the pipeline, the model needs to determine what are the possible antecedents. In the example on the slide, possible antecedents are cat and actor, but the model should also learn that only cat can be referred to by the pronoun it. We call the second step coreference resolution, where the model needs to definitively resolve the correct antecedent by looking at syntactic and semantic cues. Finally, in the third step, which we call language translation, the model needs to predict the correct gendered pronoun in German based on the antecedent. In the example on the slide, the correct pronoun is sie, because the correct antecedent is cat, and the grammatical gender of cat in German is feminine. We use our hypothetical coreference resolution pipeline as a basis for our ContraCAT template. The model we use is a concatenation model which was proposed in previous work. This model simply concatenates consecutive sentences and supplies them to a standard transformer model. In our experiments, we only use one sentence of context and prepend it to the main sentence on both the source and target side. We can see an example of this on the slide. Although this is a very simple context-aware model, it has been shown to perform very well on many discourse-specific evaluation metrics, including ContraPro. We now present the adversarial attacks we propose. For this part of our work, we take ContraPro, an existing challenge set for English to German pronoun translation evaluation. ContraPro is a contrastive challenge set where for a given source sentence containing an anaphoric pronoun it, three alternative translations are provided, each differing only in the gender of the third person pronoun in German, like in the example on the slide. Only one of these translations is correct, and the model should score the correct translation higher than the alternatives. Several context-aware models have shown very strong performance on ContraPro and other similar contrastive challenge sets. Nevertheless, we ask the following question: is this performance reliable, and can challenge scores be manipulated with seemingly unimportant changes to the input? For this reason, we propose adversarial attacks in order to test the robustness of machine translation models with regards to anaphoric pronoun translation. We propose three different adversarial attacks, which modify the full set of ContraPro examples or subsets of it. Our adversarial attacks modify theoretically inconsequential parts of the context and should not affect our model. The first attack is phrase addition, where we append or prepend short phrases containing implausible antecedents. The phrases we use are simple and can plausibly be added to all sentences. The second attack is possessive extension, where we modify the antecedent with a possessive noun phrase. Again, we introduce an alternative antecedent candidate. We expect this attack will be challenging for the model to handle. but ideally its original prediction should not change. For this attack, only certain context sentences can be modified. The third attack is synonym replacement, where we simply replace the antecedent with a synonym which has a different grammatical gender. And now for the results. We show the performance of a sentence level baseline on ContraPro in red. We show the performance of the concatenation model in green and its performance on the adversarial attacks in blue. Note that for phrase addition, we evaluate on the full ContraPro, and for possessive extension and synonym replacement only on subsets which could be reliably modified with our attacks. We see that the concatenation model strongly outperforms the sentence level baseline. However, the adversarial attacks bring down the performance substantially. For example, phrase addition lowers scores by 11% and possessive extension by 15%. These results suggest to us that the model uses brittle heuristics to solve coreference resolution. However, it is difficult to say what are those heuristics using ContraPro or our adversarial attacks. Furthermore, looking back to our hypothetical coreference resolution pipeline, it is difficult to say which steps of the pipeline the model fails to adequately handle.
Having established that ContraPro is susceptible to adversarial attacks, we develop a series of templates to systematically test weaknesses of our translation model. We call these templates ContraCAT. Adversarial attacks cannot be applied to the typical sentence and are also not suitable to test specific coreference skills in isolation. Hence, we create these templates that target each of the 3 steps in our coreference pipeline. These 3 steps are 1. Markable detection, 2. Coreference resolution, and 3. Language translation. To build our templates, we use the following entities: animals, human professions, food, and drinks. All of these can be of 3 German genders, er, sie, or es, and allow systematic modification. Animals are particularly useful since they are usually referred to with it and can act naturally both as subject and as object in a sentence. Before going into the 3 steps of our pipeline, we first tested priors. This means we looked at sentences where either 2 antecedents are equally plausible or when there's no antecedent at all. This shows us the biases of our model. Our main finding here with 3 different templates is that the model is particularly biased towards the neuter S in English-German translation. The first step in our coreference pipeline is markable detection, which should identify humans and filter them out. In the example, the cat and the actress were happy, however it was happier. Actress cannot be an antecedent as it is referred to with she. The model should therefore choose the gender of cat for translation. We now come to the second step of our pipeline, the actual meat of coreference. By this we mean actually resolving ambiguities through syntactic cues or word knowledge. For syntactic cues, we create overlap templates that are supposed to be easily solvable. Let's look at the following example. The cat ate the apple and the owl drank the water. It ate the apple quickly. The model should see that there's an overlap of the verb ate and the object apple, and it should therefore choose the gender of cat for translation, which happens to be sie in German. We also create a template for word knowledge, which is usually considered the hardest part of coreference. In the example, the cat ate the cookie, it was hungry, we know that it must refer to the cat, since a cookie, unlike a cat, cannot be hungry. Finally, we also include templates for pleonastic and event reference it. These are always translated to the neuter S in German. We expected these to be easy for the model to solve, since it already has a strong prior for the neuter S. The last step of our coreference pipeline is relatively trivial. Once the model has determined the antecedent, it needs to know the gender of the German antecedent in order to decide between er, sie, or es. Nothing else is actually required from the model, meaning it doesn't need to translate the full sentence, because this is already given by our contrastive scoring method. To test the model's knowledge of German gender, we use several thousand concrete nouns and fill the template. I saw a X, it was big, and we fill X, for example, with cat, carrot, or umbrella. Okay, so we can conclude that coreference resolution often fails when faced with our templates. More specifically, we have the following findings. First, the model is biased towards the neuter S, which even carries over to the test of markable detection, where everything is predicted as neuter S, regardless of antecedent gender. Furthermore, our overlap templates show that positioning is key for the model. Our context sentence always contains two clauses with two possible antecedents. For example, the cat ate and the dog drank. In one template, for example verb overlap template, the model might prefer the first clause, but in another template, for example object overlap template, it might prefer the second one. We also find that world knowledge proves difficult for the model. Okay, so since we can also show that the model successfully memorizes German gender, this lets us conclude that coreference resolution either fails in step 1 or step 2 of our imagined pipeline. Finally, and unsurprisingly, the model largely solves our pleonastic and event reference templates.
In our results, we observed a strong prior to the neuter S. Can we remove this prior by augmenting our training data? A good candidate for augmentation is a sentence in which there is a pronoun, it, that is not specified in the preceding sentence. For example, in the sentence, I told you before, it is red. The it is not clearly specified. This allows us to create 3 augmented training sets in German. Es ist rot, ist rot, sie ist rot. We get the following results for our ContraPro augmentations. The top row shows the original unaugmented data, and the bottom row shows the augmentations. Scores improve across the board, and also the model becomes more robust to adversarial attacks. Our template results are more of a mixed bag. While we have an improvement in markables, the scores for world knowledge and overlap show little or no improvement. Furthermore, the scores for event reference actually decrease. This is because event references can only be S, which benefits from the strong neutral prior. However, our augmentation teaches it that it can be C or S. This problem was not noted when we only did the ContraPro adversarial attacks and shows the benefits of having specific templates. While this can improve the heuristics of pronoun translation, we ultimately do not think this can solve coreference resolution based on our results. In conclusion, even challenge sets like ContraPro are subject to adversarial attacks. Our attacks show that neural machine translation uses brittle heuristics to perform coreference resolution. However, what these heuristics are and at what step in the coreference resolution pipeline this happens is not obvious. Towards this end, we create a series of templates called ContraCAT, which test the specific phenomena of coreference resolution. We also propose a data augmentation technique which can improve pronoun translation. However, it cannot solve coreference resolution. We hope we've left you with some food for thought, and we thank you for attending our presentation.